Okay, here is the version of the fundamental theorem of calculus that you will use most often. So it basically just tells you how to compute a definite integral without having to compute a crazy limit of Riemann sums. So really all you have to do in order to find the definite integral of a function is to find the antiderivative and then plug in the endpoints. Right, so in particular, we want f to be continuous on the closed bounded interval from a to b. We'll let capital F be an antiderivative of lowercase f. In other words, the derivative of capital F is lowercase f. Then the definite integral from a to b of f of x dx is just equal to capital F of b minus capital F of a. Okay, here's a quick proof of the fundamental theorem, the one that we will use most often in application. Excuse me. So we'll let f be a continuous function on the closed interval from a to b, and I'm going to let g of x be this new accumulation function based on f. So capital G of x is going to be the definite integral from a to x of the function. I should call this f of t dt. Right, so this thing is differentiable, and what's the derivative? Well, we know from the first version of the fundamental theorem that we learned, if I differentiate this thing, that's going to cancel out the integral sign, and I just replace t by x. So I know the derivative of capital G of x is just lowercase f of x. But we assume that capital F is also an antiderivative of lowercase f. In other words, capital F prime is also equal to lowercase f. So G prime and f prime are equal. And remember from the mean value theorem, if two functions have equal derivatives, they can only differ by a constant. Right? So capital F and capital G have equal derivatives. And so that means these two functions only differ by a constant. In other words, capital F is equal to capital G plus some constant capital C. So now we're trying to see what this capital F of B minus capital F of A is. So F of B minus F of A, it's the same thing as G of B plus C minus G of A plus C. And so now the C's will cancel, so this is really G of B minus G of A, but what's G of B? It's plug B in everywhere I see an X, so that's going to be the integral from A to B. So that's how I get from here to here. And then what's G of A? Well, it's plug A in everywhere I see an X, so that's the integral from A to A. But we know the integral, the definite integral from A to A of any function is 0, because this basically has 0 width and all height. So this is gone, and we're just left with the integral from a to b of f of t dt, and then if you like, the t is a dummy variable, so you can write x everywhere you see a t. So this is equal to the integral of f of x dx, and that'll do it. All right, let's compute this definite integral from 0 to 1 of x squared dx using the old method. That way we'll get a great appreciation for the new method. So we'll use right endpoint approximations using n rectangles. So remember what that is. The width is delta x, the width of each rectangle, and then f of a plus I delta x gives us the height of each rectangle using the right endpoint of each subinterval. So in this case, delta x is always b minus a over n, so in this case it's 1 minus 0 over n, which is just 1 over n. So now we've got delta x, and so we know that a in the problem, right, a in the problem is 0, and so the right endpoint approximation using n rectangles is 1 over n times the sum of f of a, which is 0, plus I times delta x, so I times 1 over n. So f in this problem is x squared, and so this all just reduces down to 1 over n times the sum right? This is just I over n, and f is x squared. So this is 1 over n times the sum, I over n quantity squared. And of course, n is a constant in this summation. It's I that's moving. And so there's really I squared over n squared, and I can write the n squared out front. So I get 1 over n cubed, the sum of I squared. So remember, the goal is to write Rn all as a function of n and get rid of all of the i's. So we've got a formula for the sum of the first n squares. That's n times n plus 1 times 2n plus 1 over 6. And so now I can exchange these two terms in the denominator. I get 1 over 6 times n plus 1 times 2n plus 1 over n cubed. And so now the degree of this polynomial in n up top is 3, and the leading term is 2. So I've got a 2n cubed over an n cubed. So as n goes to infinity, this thing will go to 2 over 1. So this whole thing goes to 1 over 6 times 2 over 1. And so we can see that this definite integral is 1/3. So now we just want to try and get the same answer using the fundamental theorem of calculus. All right, now we want to compute the same definite integral using the fundamental theorem of calculus. So in this problem, we know that lowercase f of x is equal to x squared. And so remember, to use the fundamental theorem, we need the antiderivative of lowercase f. So in this case, uppercase f. How do you find the antiderivative? You add 1 to the power and divide by the new power. So this is x cubed over 3. And so the integral from 0 to 1 of x squared dx then, it's f of 1, capital F of 1, minus capital F of 0. And so plug a 1 into this thing, you get 1/3. And then plug a 0 into this thing, you get 0. And so we do get 1/3, which agrees with the limit of the Riemann sums that we took in the previous solution.